Okay, let's talk about higher order linear differential equations. So they have a form that looks like this. So this is an order n differential equation. When I have like y with a superscript parentheses n, this means the nth derivative. So I have a function of x times the nth derivative of y plus another function of x times the n minus 1th derivative, and then I keep going. So I'm going to have a function of x times every possible derivative until I get down to, well, here's the first derivative and also the original function. And I set that equal to q. Often, and we're going to look at it this way for today, we would divide by this first function so that we just wouldn't have something there. So if I just divide everything through by p sub n, I can write it this way. And by the way, these are supposed to be lowercase p's, and above they're capital P's. So of course, when I divide by capital P sub n, like I have to divide everything by it, but I'm just going to rename this like little p sub n minus 1 and so on. So let's give this equation a name, star. And by the way, this is an exact generalization of what we learned about first order linear differential equations. For the first order, n would just be 1, so we just have the first derivative of y plus a function times y, which we normally just call p, but now we're going to call it p0 because there's a bunch of them, equals q. So this is really just a generalization of first order linear differential equations. Okay, now bear with me because there's some slightly heavy theory here, but I'll do an example at the end. Suppose these functions, like there's p naught all the way up to p sub n minus 1, and there's also little q. Suppose those functions are all continuous on an open interval I, and we have some real numbers b naught through b sub n minus 1. And suppose that little a is just any number that's in the interval I. Then there is a unique solution to this linear differential equation that I called star, satisfying these initial conditions. So in general, we've mostly done first order differential equations, and for those you just need one initial condition. For nth order, you need n initial conditions. And that's what we're using these numbers b naught through b sub n minus 1 for. So like the y of a is b naught, y prime of a is b1, all the way up to the n minus 1th derivative of y evaluated at a is b sub n minus 1. Those are our initial conditions. And what this is saying is that not only is there a solution satisfying these initial conditions, but there's only one. That's what unique is saying. And let's talk about how to find such things. So first of all, I need to talk about the homogeneous version. Homogeneous, this is kind of the same sense that we use homogeneous for like matrices, like a system of linear equations is when you set it equal to 0. That's kind of analogous here. If my little q is 0, then I have an equation and it's set equal to 0. We call that homogeneous. So first we're going to talk about the case where it's homogeneous, and then I'll talk about the general case. Here's a theorem. Suppose it is homogeneous, so suppose q is 0, and we have n linearly independent solutions, y sub 1 through y sub n, and they're linearly independent and they're solutions on the interval I. Suppose that p naught through p sub n minus 1 are continuous, then every possible solution ever to this differential equation star on the interval I is of the form, I would call this a linear combination of the y1 through yn. Let me just make this clear. C1 through Cn are real numbers. So you can just take any multiple of y1 plus any multiple of y2 plus all the way up to any multiple of yn, add them all up, and every possible solution to the differential equation can be written in that form. So that's how to find all possible solutions. By the way, even if this equation star, even if it's not homogeneous, we associate it with a differential equation that is homogeneous, and the associated homogeneous system is literally just where you replace Q with 0. That makes it homogeneous. So even if it's not homogeneous, we associate it with this one, which is homogeneous. Okay, now let's talk about how to find all solutions to a non-homogeneous one. So, what we do is we find a y sub p. P stands for particular. We find a particular solution to star, and star is the one which in general might not be homogeneous because Q could be anything. So we find a particular solution to star on the open interval I, and again, we're assuming that the P's and Q are continuous. Then every solution to star on this interval I is of the following form. I take my y sub p and I just add y sub h, where y sub h is a solution to the associated homogeneous system. And we already said how to find all possible solutions to the associated homogeneous system. That was this previous theorem, where we find n linearly independent solutions to it, and we take every possible linear combination of them. So if you take something like that and you just add your y sub p, which is your particular solution to star, then that's how you get every possible solution to star. Okay. I swear we are going to do a concrete example. One more theorem first. Yeah, here we go. We've talked about Wronskians a little bit, but this is a more particular theorem about Wronskians. If I have n solutions to double star, which is the homogeneous version, if they're linearly dependent, which is not what we want, but if they're linearly dependent, then the Wronskian is identically 0. Of course, the Wronskian is a function of x. The Wronskian is this determinant that we get by plugging in these functions, which are all functions of x, and so the Wronskian is going to be a function of x. And when I say identically 0, that means for all values of x, this function evaluates to 0 on the interval I. If they are linearly independent, then the Wronskian is never 0, meaning that for no value of x does it give you 0. So it's a pretty black and white situation. Either it's always 0 or never 0, and that tells you whether it's linearly dependent or independent. Okay, finally, let's do a concrete example. So we're going to build up our way to actually finding everything, but for now we're going to sort of halfway solve a problem. We're going to be given some information which eventually we'll learn how to find ourselves, and then for now we'll just take that information as it comes, but we'll figure out the rest. So here's an example, and this is just a second order linear differential equation, star y double prime plus 4y equals 12x. We are going to verify that y sub p equals 3x is a particular solution to that, which that'll be easy. We did stuff like that the first day of class. And we will also verify that these two functions are linearly independent solutions to the what I'm calling double star, which is just the associated homogeneous equation. Of course, it's just the same as star, except I replace the right-hand side with 0 to make it homogeneous. And that part should also be easy. We're just plugging in things and checking that it's true, but also we're going to verify that it's linearly independent, which involves finding a Wronskian. Then we're going to find a solution to star which satisfies some initial conditions. All right, so let's go. So first, let's check that y sub p satisfies star. Well, I need to know the second derivative, so, well, the derivative of 3x is 3, second derivative, 0, and so I just plug it in here. So yp double prime plus 4yp is, well, this is 0, and yp is 3x. Sure enough, I get 12x just like I'm supposed to. All right, let's check y1 and y2. Well, okay, maybe I'll just do one of these because it's boring. So maybe I'll check y1. So I need its second derivative. Well, its first derivative is, let's see, negative 2 sine 2x. And its second derivative is negative 4 cosine 2x. So y1 double prime plus 4y1. I'm supposed to check that it's 0, so here I go. So the double prime was negative 4 cosine 2x plus 4y1, and y1 was cosine 2x. Sure enough, I've got 0. These two things cancel. And like I said, you can check y2. It's just like checking y1. We are also supposed to check linear independence. And by the way, we weren't really given an interval I, but let's just say that the interval I is all real numbers. That's an open interval. All the functions involved are continuous everywhere, so let's just say that we're talking about all real numbers. Wronskian. This is going to be a 2 by 2 matrix because I've got two functions, y1 and y2. So it's going to be a determinant of a 2 by 2 matrix. And right, so I put my y1 and y2 on the first line. So that is, let's find them. Yeah, they're here. Cosine 2x, sine 2x. And then I start taking derivatives. So the next line is going to be the first derivative of these guys. So negative 2 sine 2x and 2 cosine 2x. And now I know I'm done because it's a 2 by 2 matrix. And 2 by 2 determinants are easy. I go like that and then like that. So I multiply these. I'm going to get 2 cosine squared 2x minus, and then I go that times that. So that's a negative 2 sine squared 2x. And of course, minus minus makes a plus. So actually, I've got 2 cosine squared plus 2 sine squared. And cosine squared plus sine squared is 1. So this is, here, let me actually show a little bit more work. Just in case it's not enough to say it out loud. I pull a 2 out, and then this is 1. This is cosine squared plus sine squared. So actually, we see what we were talking about, which is that the Wronskian is never 0. The Wronskian is always 2. There's no value of x for which this is 0. And that's what it's supposed to be, because these are supposed to be linearly independent, or that's what we're checking anyway. It would be weird if they weren't. We'd be checking something that's false. But it's not. We're good. So, based on the theorems that we saw, we ought to be able to find a solution, which is going to consist of a solution of the associated homogeneous equation, which is just going to be a linear combination of y1 and y2, plus my y sub p, and every solution to star can be written that way. And in particular, we should be able to find a solution to star that satisfies these initial conditions. So, okay, I have a solution to the homogeneous system, and what does that look like? That looks like something times y1, so c1 times y1, plus something times y2, so c2 times y2, and so far I just wrote what y sub h looks like. That looks like a linear combination of my y1 and my y2. And then I have to add my y sub p, which was 3x. At this point, I know that the solution I'm looking for has this form. I just don't know what C1 and C2 are, but that's what I'll find out. Well, y of 0, first of all, if I plug in 0 to here, I get, well, cosine of 0 is 1, so I'll get a C1. Sine of 0 is 0, so this doesn't do anything. And I'm plugging in 0 for x, so that's 0. And y of 0, the initial condition I was supposed to satisfy is that this should be 1. So C1 is just 1. Now let's talk about the other initial condition. Well, now I need to know the derivative. But I can take, I know my function has this form, so let's just take the derivative. So this is negative 2c1 sine 2x plus 2c2 cosine 2x. And I've got to take the derivative of this too, so 3. Now I'm ready, because this initial condition tells me y prime of 0 equals 3. So let's plug in 0. Sine of 0 is 0, so this doesn't do anything. Cosine of 0 is 1, so I've got a 2c2 here, plus 3 equals, well, it's supposed to equal 3. And now I know C2. So the solution I'm looking for is just this, but I plug in C1 and C2. And C2 was 0, so I'll skip it.